Charged Tapes Lab by Drew Peldrovich. What is the experiment? The experiment consisted of charging pieces of Scotch tape and observing their interactions to determine the charge on one piece of tape. The dimensions of the tape were the length being 0.02 meters long, the width being 0.019 meters wide, and the density of 1 gram per 1 meter. To get mass, simply multiply density by length to get 0.02 grams for each piece of tape. To check if the tape was charged, I placed my neutrally charged hand near the tape, and since the tape was attracted to my hand, I knew the tape was charged. Furthermore, when two pieces of tape were placed next to each other, they repelled each other, indicating that they have the same charge. And when the two charged tapes were placed on top of one another, the higher tape began to float when they were just 0.02 meters of separation away. To determine whether the tape was positively or negatively charged, I conducted the pen test. First, I rubbed a plastic pen on a piece of cloth and created a negative charge on the pen. Then I brought it near the tape to see whether it would attract or repel. Since the tape was attracted to the pen, and the pen was already determined to be a negative charge, I reasoned that the tape had a positive charge. To calculate the forces on the tape, I started with gravitational force. Using the equation F equals mg and substituting the values where mass is 0.02 grams and gravity was 9.8 meters per second squared, I got the answer that the force was equal to 0.196 newtons. To get the electric force, I used the fact that according to the free body diagram of the piece of tape, electric force and gravitational force were equal and opposite in direction. So, electric force was also 0.196 newtons. Using this data, I was able to calculate the charge on one piece of tape, using the equation q squared over 4 pi epsilon naught d squared equals the gravitational force, which was already calculated to be 0.196 newtons. Solving for q, I get a value of 9.33 times 10 to the negative 8th. And taking this value and dividing it by the charge of a single electron, I can calculate that the number of electrons on a piece of tape was 5.833 times 10 to the 11th. However, given the fact that an atom has an approximate length scale of 1 times 10 to the negative 10th of a meter, and using the fact that the length of the tape was 0.02 meters, I can divide 0.02 times 1 times 10 to the negative 10th to get an estimate of around 200 million atoms on a piece of tape, which is far different from the calculated value of 5.833 times 10 to the 11th number of electrons. The difference in these numbers could be due to rounding errors or measurement errors, since the ruler in between the two pieces of tape was not completely accurate. The computational model of the tape can be seen on this slide, with its 3D model shown as well. According to the computational model, the charge on the tape was equal to 9.33 times 10 to the negative 8th coulombs. In order to make this calculation, several assumptions were made. The first being that I had to treat the tape as a point charge, with all the charge concentrated at its center. And the second assumption was to assume that each tape had the same amount of charge and that it was evenly distributed along the length of the tape. Some other thoughts. If the electrons and protons suddenly switched charges, that is, the protons were suddenly negative and the electrons were suddenly positive, the experiment would almost be the exact same. Since the tapes were created in the same way, they would switch from both having a positive charge to both having a negative charge, and they would still repel each other since they would still be the same. If the pen were to suddenly switch from having a negative charge to a positive charge, the tapes would still attract it because the tapes would now both have a negative charge. However, if the tape stayed negative and the pen stayed negative, then the tapes would now repel the pen since they had the same charge. Also, it's important to touch the tape as little as possible because hands are neutrally charged objects. So the more time in contact with the tape, more of the negative charges on the hand would flow to the positively charged tape, eventually making the tape as a whole neutrally charged and ruining the experiment. In conclusion, the lab taught me how to calculate the charges on the tape, and using observations and computer modeling, I was able to provide a rough estimate of the actual experiment using code. Then, using that same code and some equations, I was able to gather data on the tapes to determine their charges and the forces acting on each one.